Hello and welcome back to this series on Python and performing OCR in Python. This tutorial series is geared towards anyone with a general understanding of Python that wants to perform OCR in it. Now, in the last video, I introduced you to a fairly simple library for loading images into memory, and that was Pillow, or the Python Imaging Library. The Pillow is just a fork of Pill. What we're going to cover in this video, however, is a different library called OpenCV, which stands for Computer Vision. Computer Vision is a complex task that requires you to manipulate images or video feeds really in complex ways. Now, the benefit of a library that can achieve that is that you can do really complex image manipulation in Python. The downside to that, like any other programming language or software out there, the ability to perform really robust tasks means that the ability to actually do those tasks in code or in the program is necessarily a bit more complicated. And it's no different with OpenCV. What I'm going to do in this video is I'm going to walk through all of the key steps to image processing to get better results with PyTesseract or Tesseract in general with OpenCV. And these image manipulation steps are usually something I would cover in individual smaller videos, but because I want you all to use this video as a one-stop shop, I'm making an exception here, and this is going to be an exceptionally long video, but I'm going to have everything timestamped in the bottom down below in the description so that you can skip to the task that you need a refresher on. I encourage you for the first pass of this video to sit back, grab a cup of coffee, and just watch, because I'm going to be going over 9 different main ways you need to manipulate an image or could need to manipulate an image in Python to have better OCR results with Tesseract. So the first thing we're going to talk about are inverting images and why you might not want to do them in Tesseract 4. We're going to also talk about rescaling, which is when you adjust the DPI of an image, which is going to be necessary for some images. We're going to talk about binarization, the conversion of an image to black and white. We're going to talk about noise removal, which is what it sounds like, the removal of noise from an image, which can oftentimes produce poor OCR results. We're going to talk about dilation and erosion, and you'll see what that is. This is when you have bleeding of text in old historical documents, and this is a way to kind of eliminate that, which will improve OCR results. We're going to talk about rotation and deskewing. This is oftentimes the result of a bad scan when the page is at an angle. We're going to talk about removing borders. This is one of the best steps you can do. Oftentimes you can have a very, very clean page and a single black border will ruin everything for you. We're going to talk about how to remove those borders. And then also the inverse problem, missing borders. We're going to talk about how to add borders in so that you can have better results. And then we're going to talk about some unique cases where transparency and alpha channels might affect your OCR results. I'm going to cover each of these in this Jupyter notebook, which I'm going to put onto GitHub so that you can actually go in and use this as a cheat sheet if you want, copy and paste things from here and use them in your own scripts. But I encourage you to sit back and watch all of these steps, because not all these steps will be relevant to you right now, but they will be in the future at some point. At some point, you're going to be working with a document that was very badly scanned and you need to rotate it and deskew it. At some point in the future, you're going to have a scan that's got borders that you're going to have to remove. You're going to have to know how to do all these things to solve different OCR problems during the course of your career. So you're not going to have to do all of these for a single task, but you're going to have to do all of these at some point for different tasks. That's going to be what we cover in this video moving forward. But before we get to that, the first thing we have to talk about, and this is why it's 00, is how to open an image in Python with OpenCV. So the way in which you open a video or an image file in Python with OpenCV is we're going to say create an image name. Let's call it image underscore file. This is going to be the location of our file, and we're going to be referring back to image underscore file throughout our script. So we know that our image is in data, and it's page underscore o1.jpg. So page underscore o1.jpg. So it's a JPEG. And then what we need to do is we need to load that image file into memory. Now, there is a bunch of different ways to actually do all of this in Python, or Pythonically. Some people will say im, other people will say img, others will spell out image. And the problem with this is that OpenCV's documentation is oftentimes neglected. Speaking of which, you need to actually import OpenCV. And now if you look at OpenCV's documentation, you'll notice that they say import CV2 as CV. Let me zoom in a little bit for you. The problem with this is that the community has not done this. So what I'm going to do is I'm going to do what the community does because it'll make your life a lot easier. And we're going to import CV2. We're not going to import it as CV. Now, I personally think that one should follow the documentation. I am making an exception here because anytime you try to look for a problem with OpenCV on Stack Overflow, everyone's going to be doing import CV2, or at least a lot of them. So once you've got that loaded, now it comes time to create the image file, to load the item into memory. And we're going to do this by saying CV2 dot im, so image, read, and we're going to pass in one argument right now. Now there's multiple parameters that you can pass here. We're going to pass in our image file. And when you do that, you've loaded it into memory. And I got a syntax error because I forgot to hit equals. There we go. Now, if I'm working inside of Atom, I can show an image in a very specific way. I can say cv2.im show, it stands for image show. I'm going to pass in two arguments. Think of this as a title, so original image, and the next thing I would pass in is the image itself, img. Then what I can do is I can say cv2.wait, capital key, and this is going to allow for it to wait. Now I can specify in milliseconds how long to wait for. So 100 milliseconds would be 100 milliseconds, or I can do 0, which will be an indefinite amount of time. If I execute this, you'll see that I have an error. CV2 is not defined. Let's go ahead and start this. There we go. And then I can open it up. Now, because I am using Jupyter Lab, you'll see that I can actually open up the image. If you're using Jupyter Notebooks, not Jupyter Lab, your Python might crash. And if you're going to do that, you're going to have to do something like cv2.destroy all windows. There's a couple little hack arounds. What I'm going to do, however, is because I want to display inside of Jupyter Notebook, I want to be able to display the image in line, meaning I want to be able to see it all the way through. I'm going to use this function that I found on Stack Overflow, and I'm going to include this in where I got it from right here. So this is the link. And this is a handy way of using matplotlib to actually show what's happening. Let me try to get over that way. There we go. And I'll just put it down there. To show what's happening in line from OpenCV. And so I've added this little bit up here, from matplotlib import pyplot as plt. So what I can do now is I can execute this cell. So I've loaded that function into memory. And what this function is going to do is it's going to allow for me to maintain the original image size as I use matplotlib to kind of display it. Now what I can do is I can just use one simple function to display my image. And this function is called display. So I can say display, and then I can pass in, this is going to take the path. And my path is image underscore file. I can run that. And then I can display the image in line. Now I have the full proper resolution of the image. So it's a bit large for this video, but I think it's important because if I didn't do this, and if I were to just use matplotlib, it'd be a very small file, and it would be also difficult to actually decipher the actual characters or the words, the letters in this image. So this is the original image that we're going to be working with throughout this script. What we're going to be doing now throughout the rest of the script is we're going to be following these 9 steps to invert the image, to rescale the image, to binarize, noise removal, etc. on down the list. In other words, we're going to be using OpenCV to manipulate this image. And then at the end of this video, we're going to create functions to do all these different steps. At the end of this video, we're going to display all of these images side by side in a 3x3 column with the original image up above. And that's going to allow us to see how each of these steps affects our output a little differently. So we're going to be trying to get rid of borders. We're going to be trying to clean up some of this noise. We're going to invert it. We're going to convert it to black and white all in the next few steps. So let's go ahead and start with inverted images. So our first task is going to be to invert an image. An inverted image is kind of what it sounds like. It's when you take all the different pixels and you make them the exact opposite of what they are. So things that are in the white spectrum will become black. Things in the black spectrum, so grays, dark grays, blacks will become the opposite. So their inversed counterpart in the white spectrum. This used to be a great way to pre-process an image for OCR and Tesseract with Tesseract 3X, so Tesseract 3.0. If you're using Tesseract 4.0, this actually will return poorer results. And the way in which you pre-process an image is to get the image into the optimal shape or optimal way so that it can be processed the way the training data was processed. So the way the system learned on the types of images, that's how you want to kind of get those images to the OCR system. So even though this is irrelevant for Tesseract 4.0, I still want to show you how to do this because this is an important step with certain cleaning methods. So how do you do it? Well, fortunately, there is a built-in way, and you can do this with OpenCV. So what we're going to do is we're going to create a new object. We're going to call this inverted image, and we're going to make that equal to cv2.bitwise, and we're going to pass in img, our image, if you remember, that we loaded in up above right here, this img. So let's scroll back down. And then what we're going to also do is we're going to save that file into our temp data folder so that we can then display it with our function that we wrote up above. So what we're going to do is we're going to say cv2.imwrite, which is going to allow us to write that file somewhere in our directory. And we're going to say where we want to write that to. So we're going to say temp/inverted.jpg, so JPEG. And then we're going to say what that file is. We want to save our inverted image. And if we do that, we see that we've got an attribute error. So bitwise is, I forgot to do bitwise underscore not. There we go. And it comes back as true. So we've now officially saved that file. Now let's use our display function to display it. So we're going to call in that temp inverted.jpg. And we're going to run this. And now we have an inverted image of that original file. So our original is up here, and we see that the inverted does exactly what I said it would do. All the lighter areas are now dark. All the darker areas are now light. This, however, is not an essential step in Tesseract 4.0, but that it's an important skill to understand how to implement. The next thing I want to look at is something known as rescaling. Now, I'm not going to do a lot with rescaling right here because it's really difficult to do well, and it's not going to be entirely necessary. Essentially, there is an optimal range for your image file to be in for it to have optimized OCR. And that range is going to be defined by the height of the characters, which comes down to the DPI. This is in the Tesseract OCR documentation. I'm going to address this in a later video because it requires a bit more knowledge of OpenCV to do it well. And we're not there yet with this series. I am going to, however, fill this in when I put the Jupyter Notebook onto GitHub, so you'll be able to see that. We're going to skip that just for right now, and we're going to jump down to binarization. Binarization is the process in which you binarize or convert an image into black and white. Now, in order for an image to be converted into black and white, well, it needs to first be in grayscale. So the first thing we need to do is we need to create a function that's going to automatically convert for us our file, our image, into grayscale so that we can then save that gray file and then use that gray file to do binarization. So first, let's tackle the first problem, a function to get our image into grayscale. So we're going to call this grayscale, and actually we're just going to call it grayscale. And what we're going to do is that we're going to say this is going to take a single thing, and that's going to be the image itself. And then what we're going to do is we are going to just return, we're going to return cv2.cvt color with a capital C, and we're going to convert that image. This is going to take two arguments, the image and then how we want that image to be converted. And this is going to be the part of OpenCV's syntax. It's going to look a little odd to you if you're not familiar with it. We're going to say cv2 dot, we're going to say capital letters, color underscore BGR to the number 2 gray. And what that's going to do is it's going to return for us a gray scale image. So let's go ahead and just save that function there. And now let's create that gray image. So we're going to create an object called gray underscore image, and we're going to make this equal to grayscale img. So we're going to pass that object into it. And then what I want to do is I want to say cv2.imWrite. So we're going to write an image now, again, into our temp folder. This is going to be our grayscale image. We're going to call this gray.jpg. And we're going to make sure that that is the gray image. And if we execute this, everything works great. Everyone's happy. We got true. Means our image is now saved. Let's go ahead and display that that image. So we're going to display temp_gray.jpg. And let's display that and see what it looks like. This is now a grayscaled version of our file. And if you saw it side by side, it doesn't look too different, but you'll notice that the tans, or the hues of tan, so the beige colors, are now grayed out. This is what the grayscale image looks like. Now that we have a grayscaled image, it's time to actually binarize that image and convert it into some kind of strictly black and white. And the reason why you want to convert to grayscale first is it's going to allow for this process to be done a lot more easily. And so what we're going to do now is we're going to say thresh, im_bw. This is going to stand for threshold and image black and white. This is the Pythonic way to do it. We're going to make that equal to cv2.threshold. So this is how we adjust the threshold of an image in OpenCV. And we're going to say gray image. So the first object, or the first parameter here, the first argument needs to be the image itself. And then we're going to have two integers. I'm going to explain these integers in a lot more detail later on. For right now, just understand these will control the threshold and the range. Oftentimes, you're going to start off with 127, and you're going to start off with 255 here. I'm going to explain why with text, this isn't always the right parameters here, and I'm going to be adjusting this in just a second. This is just to demonstrate what's going on. The next thing we're going to say is cv2.thresh. This is going to be all capitals, _binary. There's about 6 or 7 different ways of adjusting the threshold here, and I'm not going to address all of them right now because we're just trying to get the basics of this process down. Once we've done that, we can now say cv2.imWrite. We're going to write the im_bw. We're going to write that black and white image down. So to do this, we're going to say temp_bw, bw image. So the black and white image.jpg. And then we're going to say that we want it to be the imbw. Let's go ahead and run that and make sure everything comes out correct. And it does. Now it comes time to display it. So now we're going to display temp_bw image.jpg. And what we're going to see now is a black and white image. Now I want you to take a moment and look at this. Does this look like a good result? The answer is no. But what's interesting is that while this is more difficult for us humans to read, certain things might be easier for a machine to read. But right now, we don't have the correct keyword parameters. We don't have the correct parameters here. And instead, you want to adjust this to somewhere probably around for this, let's say 200 and 230, and rerun these two cells. And now you get something that looks like this. What you have here is a much better result. In fact, you're probably going to want to play around with these numbers a little bit more, but what you're getting now is an image that does not have a lot of the noise that is going on that you saw in the original image up here. All of these little pixels of hues and all these different things throw off OCR radically. Now with this particular image, we could probably run this through PyTesseract without any kind of manipulation and have fairly good results. But we're not after fairly good, we're after great results. By doing these kinds of pre-processing things to our OCR or to our image file, we are going to have much better results with the OCR process. And that's because we're able to contrast the actual script here, the actual font, the actual characters on the page. We can contrast them much better because we've made that background, that all those different colors of beiges and shades of dark colors are now one color, and that's bright white. And the same thing has happened with our actual pixels that represent the characters on the page. They're now a dark black. This is going to allow for much better OCR, and I cannot stress to you enough that this right here, this conversion to gray and this conversion to playing with the threshold to create a binary image, this is the most important step throughout all of these next few steps I'm going to be showing you, is getting a good binary image. And you're going to want to play with these numbers a little bit to get something that works best for your image at hand. But as we're going to see, there are different times when different methods are going to be necessary. And what we're going to be looking at over the next few minutes is, what do we do about images that might have a lot of noise in the background? How do you remove that? That's going to be what we look at now. So what we have now is a fairly good image. But one of the things that if you look at this image, you might immediately notice, though you don't know the word for it, is that there still remains some noise. What is noise? Well, noise is anything like this: pixels that do not correspond to text that are still surrounding certain text items. So this would be considered noise down in the bottom right-hand corner, these pixels surrounding the number 1, but you're going to really have a problem with things like this. Now, truth be told, this right here in this state is good enough to get state-of-the-art OCR results. And when I say state-of-the-art, I mean 98th percentile range. This is good enough. However, we can do better. And the reason why I'm going to take the steps to show you how to do this with this document, even though it's in a good enough state, is because not all documents are created the same. Some documents you're going to find are going to have a lot of noise around them. And what I'm going to show you in this video is how to get rid of things like these dots around the word internal and affairs, these little dots down on here. And we're going to do this using a method that we're going to see in a lot more detail in just a second. And we're going to use dilation and erosion. In order to do noise removal, we're going to create a new function. Let's call it noise underscore removal. This is going to take one argument. It's going to be the image that we pass to it. Now, within this function, we're going to have to import numpy. So we're going to import numpy as MP. NumPy is a way of working more efficiently with numerical data in memory because of how it's stored. I'm not going to get into it in this video. Understand that it is an essential component of most machine learning and most robust libraries in Python. So we're going to have an object called kernel, and this is going to be equal to np.ones. And we're going to pass in the size for our first argument of the actual kernel. This is going to be the, kind of think of it as the shape of how we're passing over and capturing noise. And the second argument is going to be np.unit, int, there we go, 8. Next, what we need to do is we need to start adjusting that image based on these kernels. So we're going to say image is going to be equal to image. So we're going to, image is going to be equal to CV2 dilate. So we're going to use the CV2.dilate. And we're going to make this equal to, or have a few different parameters here. The first thing is going to be our image that we're passing to it. The next is going to be the size of the dilation that we want to see, and that's going to be our kernel. And the next is going to be a keyword argument called iterations. We're going to make that equal to 1, so just 1 pass over the image for dilation. Next, we need to have really another kernel, because you might, let me make this an E actually. There we go. That way it's Pythonic. The other thing that you would want to have is another kernel that will affect the dilation of the erosion. Now, you're going to want to keep these, in my case right now, the same because they're going to be doing the exact same thing. But in certain problems, you're going to want to have these be different sizes for different tasks. Just for right now, we're going to kind of repeat all these same things. The second parameter here is going to be np.uint8. And what we can do now is we can do image equals, we're going to modify the image once again, and this is going to be equal to CV2 dot, and we're going to say erode this time. And the erosion, the erode class is going to take a few different things. It's going to take the image, just like we saw before. It's going to take the kernel, and then again, we're going to have iterations equal to 1, and that's going to erode the image a little bit for us. The next thing that we need to do is we need to morph the image. So we're going to say image is equal to cv2.morphology, capital E here, x, lowercase x. And we're going to say image, and then finally our second thing is going to be cv2.morph close, all caps here, all caps, very important. And next we're going to say kernel to capture that, that size once again. And then next we're going to say image is going to be equal to CV2 dot, and we're going to blur it a little bit. We're going to say median blur. And again, think of all these things like the different steps you might do like in Photoshop or some kind of image processing library. And finally, we're just going to take a second argument that's going to be 3. Again, these are controlling the shapes of these things, the shape of the blur. And then we're going to return the image. So this is going to be our steps for noise removal. Now, in order to actually bring in that noise removal and execute it, we need a way to essentially write it down into our temp folder. So let's say no noise, this is going to be our new object, is going to be equal to noise removal. Now here we're not going to say image. We're going to now grab this black and white image that we created up here. So that's im_bw. And then what we're going to do is we're going to write it. So we're going to do cv2.imWrite. Now we're going to write it into our temp folder once again. We're going to call this no_noise.jpg. And that's going to be our no noise right there. And let's go ahead and load that function into memory, execute that, and we've got an error. CV2 morph, what did I do wrong? I think I spelled morphology wrong. Let's see. Morphology, there we go. Now we should be good. There we are. And we get the true back, so everything's worked out great. Now let's go ahead and display this file. We're going to display temp no noise.jpg. And let's see what it looks like. And this is now what our image looks like. I want you to have a particular note here on all of this noise that's down here. 1 is now appearing without any kind of stuff around it. If we scroll back up, you can see that 1 was clouded with a whole bunch of noise. Now, like I said, for this particular problem, 1 would have probably been captured perfectly without issue. Same thing with internal and affairs, but let's look and see for a second what we've done. All of that noise surrounding internal and affairs is now gone. However, it came at a cost, and that cost was that our characters are now a little bit more emboldened. If we look back up here, you can see that internal is a little bit more legible here. In this instance, I probably would not have done noise removal. I would have done a test by passing this image to PyTesseract, and if it came back perfectly fine, I wouldn't have done noise removal. If, however, this noise was throwing off PyTesseract, I would then move to the noise removal step in order to actually get rid of that noise, because this is a better result if it's illegible. Okay, so what do we do about texts that have really thick letters that might throw off OCR results, or maybe really thin letters that might throw off OCR results? The answer comes down to the 2 things that we just saw a second ago that we're now going to dive a little bit more into, and that's dilation and erosion in OpenCV. So let's scroll down and let's start working with dilation and erosion. So when you want to use dilation and erosion on their own without the morphology X and the median blur is when you don't have noise in the background. These are the main things that get rid of the noise, the morphology X and the median blur. When you don't have noise in the background, but you've got font that looks a little too thick or font that looks a little too thin, you can use the dilation and erosion methods in OpenCV to actually adjust the font sizes. So let's go ahead and look at a function to make let's try to make our font size thinner. Now what you're going to see in this process is we're going to make it where it's actually worse. I would consider this font at this stage to be fine. It'll work perfectly fine in PyTesseract right off the bat. But let's try to just experiment with thinning the font and thickening the font so that you can be able to do that with a problem that might require it. So what we're going to do is we're going to create first a function. We're going to call it thin font. Not a very clever name, but one that'll work for us just fine. What we're going to do is this is going to take, again, just one argument. That's going to be the image itself. And we're going to import numpy as MP. At this point, I should probably just have that at the top of the script. We're going to say image is going to be equal to, and this is going to be where we set kind of a new image here. Now, in order for dilation and erosion to make sense, they're kind of backwards. And the reason why they're backwards is because they're meant to handle an image that has The background, the surface is black, and the font and the text is white. So what we need to do in order for the dilation and erosion to make sense is we need to convert our image into black and white, or sorry, we need to invert our image. Now I showed inverting an image up above. Essentially, you use cv2.bitwise underscore not image, and that's going to make our image now the exact opposite. What we're also going to do is we're going to use the same kernel that we saw up above, except this time we're going to make a kernel size of 2,2. And then what we're going to do, and this is going to be the new part, we're going to say image is going to be equal to cv2.erode. So we're going to erode the image. This is going to thin the text. Erosion is thinning of pixels down. We're going to say image kernel, and then we're going to say iterations is equal to, we're just going to do 1 here. And then what we're going to do is we're finally going to reconvert that image from, revert it back. So we're going to do an inversion once again. So we're going to say image is going to be equal to cv2.bitwise underscore not image. And that's going to revert it back to white being the background and black being the font. Then we're going to return image. And once we have that function loaded, we see that it's going to work just fine. It's time to make our eroded image. And we're going to make this equal to thin font, and we're going to pass in our, pass in our no noise image. So we're going to pass in this image right here, the one that we just got no noise from. And what we're going to then do is say cv2.iamWrite. We're going to write the image, the eroded image, to temp eroded image.jpg. And that's going to be our eroded image. Let's run that cell, and we see true, fantastic. And now let's display it. So we're going to say display temp \eroded image.jpg. And we're going to execute that, and you now see that the font is a lot thinner. Now I can up the kernel size to 3. It's going to start becoming a little illegible here, and I would argue not good. So let's change that parameter there. Rerun these cells, why not? And we see that we have something that looks like this. This is not good. You could also play around with the number of iterations that you do with this. So we can make it where it's, let's make it 10 iterations. So 10 passes over that. And you'll see something that looks like this, where it's just a completely white page because it's gone through that same process twice. But you get the idea. You can play around with these numbers, and every single OCR problem is a little bit different. Now, I would argue that this is not good, and it's not. The other thing that we can do, let's go back to 1 and adjust this down, is we can also thicken our images. And the way in which we can do that is by, let's go ahead and just, let's create a few new cells here. And we're going to copy and paste this down because we're only going to be changing really one thing from this function. We're going to call this function thick font. Thick font. Again, it's going to do all these same things, except here we're going to say dilate. Dilate is the expansion of pixels. So in this scenario, we're going to expand the pixels. And so for that, let's say dilated image, and that's going to be equal to thick font. And we're going to pass in the same im underscore bw, or sorry, the no noise image is what we're going to pass to it. And then we're going to say cv2.iamWrite, and we're going to write this as temp dilated image.jpg, dilated image. And then we're going to execute that cell, true, great. It looks like that function works just fine. Now we need to display it. So we're going to say display, and that's going to be equal to temp \dilated image.jpg. And then we execute this cell, we'll see a thickened font. Now, in some cases, this is going to be an essential step. If you notice, this is going to be particularly useful for problems like we saw here, the 1944. You can see how the 44 there doesn't look as clear as the 44 down here. So in some instances, you can see why the thickening of a font might be essential. Let's scroll back up to this. You'll see it's looking a little bit better than it did before. Just a little bit, not a lot. Again, because this is not an image that requires a lot of these processes. And you're going to find that when you're working with a large PDF that has a large set of similar documents, you're only going to have to find the sweet spot just 1 or 2 times. and adjust accordingly. So this is kind of how you solve a problem of too small a font and too large a font using erosion and dilation. And it is important to remember that these processes will work in the opposite order unless you bind or invert the images at the beginning of the function and at the end of the function. So in the next thing we're going to talk about is rotation and deskewing. And for this, I'm going to have to use a different PDF, a different image, because this honestly is not bad enough where I could even justify using it. You're going to want to use rotation and deskewing when you're dealing with a PDF or an image file that is pivoted sideways. In fact, one of the things I might do is I might just go ahead and load in this image skewed so that we can then deskew it. Okay, now that we have gone through and shown you how to kind of do these different methods for expanding or contracting with erosion and dilation, it's time to show you how to do some really important stuff with a lot of bad OCR'd images, or a lot of bad images of text. And one of the common problems that you'll see with images of text is that you're going to have pictures that look like this. Now, this is the exact same file. All I've done is I've just rotated it, and this is important to note here for this method to work. I've already eliminated the borders. I'm going to be showing you how to identify and delete borders in the next segment of this video. For right now, however, we're going to focus on just how to handle a rotated text. The reason why rotated texts will not be picked up is because of one very important thing. It's how OCR works. OCR is designed to work with vertically aligned text, meaning it expects for the images to look like this with the text straight up. One of the things you're going to have to do as part of your pre-processing is take in images frequently that look like this and correct them. Now, I'm going to be copying and pasting in some code here from a website. I did not write the code that you're going to see here in just a second. I'm going to copy and paste the functions in, but I'm going to explain essentially how it's working and why it does what it does and why it's an important step. So let's go ahead first and foremost and load in our actual image. We need to load in this page underscore 01 underscore rotated.jpg. So the way in which we're going to do that is we're going to create a new image. Let's just call it new. We're going to keep this very simple, cv2.imread. So this is the same syntax that we saw up above, and this is located in data backslash, and it's going to be page underscore 01 underscore rotated.jpg. Now let's go ahead and load that in. It's now loaded into memory. Fantastic. Now I'm going to copy and paste this code in. I'll go through real quickly and explain what's happening and why it's important. So it's a lot of code to go through. So what we're doing is we're importing NumPy, same thing that you've seen before. And what this function does, and I'll give you the source for it right here as well. It's from becominghuman.ai. And from what I have seen across the internet, this solution is fairly common, and it is, scroll back up, and it's used by a lot of different people in a lot of different places. I don't know if this is the original source for this code, but this is where I initially found it. That's why I'm providing it. You will see it in other places. So what this does is it goes through and it processes the image, and it grays it, it blurs it, it adds a threshold, and it adds a really large blurring effect to it so that you can identify contours. Now, contours are going to allow you to draw bounding boxes. I'm not going to talk about bounding boxes in this video. I will, however, give you a quick little glimpse at what a bounding box will look like on an image. So this is the image, and this is the way bounding boxes work. Now, if you notice, the bounding boxes are angular, so they're not actually able to capture text in a horizontal way. What we're going to do is we're going to use things like that in this function to make a prediction about how the text ought to be laid out. And that's essentially what this function does. It captures the angle of the text and makes an automatic guess about how best to adjust the image to capture the correct rotation. And it's, again, very important for this that you do not have a border. That's very important. If you have a border, you will have problems. Removing borders should occur first.
So now that we've got this function and everything loaded into memory, it's time to actually use the function. And what's nice and handy about this is that we can do a lot of very complex things with, let me add one more function in, there we go. We can do a lot of very complex things with really just one line of code now. So we can call this new object fixed. And we're going to make that equal to dskew. So we're going to call in this new skew function, dskew function, which is going to run all these functions, call these other functions up here, and it's going to essentially output an image for us. So this is going to take in new, that image that we loaded in up above, the one that is skewed. And what we're going to do is we're going to say cv2.imWrite, and we're going to write that that fixed image to our temp folder, and we're going to call this, let's call it temp, I think I've called it rotated fixed.jpg. And we need to pass one more argument, and that's going to be the object itself, and looks good there. What we're going to do now is we're going to do display. We're going to display that temp \rotated fixed.jpg. We're going to display it now. And now look, we've taken that rotated image. In fact, let's go ahead and display that rotated image up here. So you can kind of see them right next to each other. We're going to do display data page 01 rotated.jpg. There we are. Let's go ahead and load that in. So it looks like this initially, right? Definitely skewed, definitely slanted. What the function has done is it's taken it and twisted it around for us based on the bounding boxes, based on the contours it was able to identify. I cannot stress to you all enough how important this function is for having better OCR results. You'll be very happy. It will save you lots of time of scouring the internet trying to find a solution to a deskewing problem that you can just copy and paste this code in. Again, I've given you the source if you want to explore the blog on this a little bit more, but you'll find it in multiple places across the internet. Now, if you notice, you look really closely, you'll see something that's happening here. It's blurring. If your text, like for example, if that were cropped like right there on the side, that little letter would be skewed a little bit. So you want to make sure that if you're dealing with text where the text is butting up against a border, you're going to want to also add in a little bit of a border around your picture as well, or around your image as well. Again, we're going to be dealing with removing borders and missing borders right now. Okay, so now we're going to try to remove some borders. I'm going to be working with the no noise image that we saw just above. If you don't remember, I'm going to go ahead and display that image right now by typing in display. And we're going to do temp \no noise.jpg. And we're going to be able to see what this no noise image looks like. And if you notice, we have a very clear black background. Ignore this white bit right here. This is just the Jupyter Notebook's rendering of its own border. But the actual border within the image itself is right here and it's black. What we're going to do right now is we're going to try to eliminate that border. We're not going to be able to get all of it with this method. I'm going to show you another method in a later video using bounding boxes in a more robust way where we can achieve this, when I talk about bounding boxes in more depth. For right now, though, we're going to get rid of most of it. And the reason why we can't get rid of all of it is because of this little bit over here on the right-hand side. It is uneven. The border is uneven. It's not a straight shot. And that's going to cause a little bit of this border to remain with this method. But let's go ahead and jump right into it. What we're going to do is we're going to create a function here. Let's get creative and call it remove borders. It's going to take one argument. Once again, this is going to be the image that we're going to work with. It's going to be in this case, the no noise image that we're going to pass to it. Now we're going to have two arguments coming out, or two objects coming out of this one line of code here, which is going to be cv2.find contours with a capital C there, very important. And we're going to pass in the image, and then we're going to do cv2.retr_external, cv2.chain underscore aprox underscore simple. I'm not going to explain too much about what's happening here, because what we are dealing with is something that is beyond the scope of this video. I'm just trying to give you the code necessary to achieve this task. The next thing that we're going to do is we're going to sort out CNTS sorted. This is going to be the contours sorted out. We're going to make this equal to sorted, And again, we're going to be using something a little bit beyond the scope of this video, which is going to be lambda. I'm not going to cover lambda right now, but essentially this is going to allow us to organize all of our contours, all of our little bounding boxes that we're going to make here into a nice sorted list based on size. Area, and we're going to pass in X. And then what we need to do is we need to grab the last item in that list, because the last item in that list is going to be the largest. It's going to be the largest bounding box, which means it's going to be the bounding box that covers this main block of text. Everything else is going to be small little things, like maybe that bit there, maybe that bit there. I'm not entirely sure what it's going to grab, but I know that the largest thing is going to be all of this white area. And then what I need to do is I need to do x, comma y, comma width, comma height, w and h. We're going to make that equal to cv2 bounding rect, and we're going to pass in that one contour, that one box, which is going to be, like I said, the largest box that we have. And we're going to set crop equal to image, and we're going to crop the image down. This is how you crop an image. You're going to say y colon y plus. I always have to cheat with, I got a cheat sheet on the other screen over here because I have a very hard time remembering the proper syntax for OpenCV. This is not a very, in my opinion, not a very natural library. I have a hard time remembering the syntax, and I'll provide a link in the description down below, some good cheat sheets for these basic lines of command, but I oftentimes find myself going to Stack Overflow for a lot of this. Multiple times when I'm working on anything with OpenCV. So this is our function. It's going to return a cropped image, essentially. Now, if you're dealing with PDFs where the margins, the borders are consistently the same cropping on any side, do not use this method. Pre-process them with a PDF editor or an image editor to edit in bulk if you already know the determined size. Otherwise, you can, if you know the determined size in numbers such as width, height, X and Y, you can go ahead and do that in OpenCV as well by passing in those arguments manually. What this is doing is it's creating those bounding boxes and finding the borders automatically. This is particularly good if you're dealing with inconsistent borders across images that you're trying to OCR. So we're going to make another object called no_borders, and this is going to be where we call in our function remove borders, and we're going to pass in that object of no noise. And then what we're going to do is we're going to say cv2.IamRight. We're going to create this no borders temp file like we always have done in the past, no borders.jpg, and we're going to pass in the other argument, which is, you guessed it, our object. And then what we need to do is display temp no borders.jpg. Now, if I've written this function correctly, it looks like we've got an error here. Find contours. Oh, counters. Contours, there we go. I might have another error. CV2 has contours area. What have I done wrong? Contour area is what this should be. I apologize there. And then we have got, it's not defined. There we go. I forgot my S right there. And looks like I have, yet again, another error. It looks like I haven't done cv2.bounding rect. I apologize sincerely if you followed along with that. But as you can see, once you've achieved this, we've gotten rid almost of all of the borders. Like I promised you, there is a little bit still here because it was not a straight shot. There are other methods to get rid of the text around the borders, specifically to grab paragraphs. In this scenario, if you're trying to automate the process, I would not use this method. I would use bounding boxes to grab the main body of the text. I'm going to cover that in another video because this is strictly dealing with the pre-processing of the image as a whole to get better OCR results. So that's going to be how you remove a border. Now we need to talk about how to add in missing borders. Now, why should you do this? And you should do this in certain circumstances when your text is all the way up against the border. So it's when the image is cropped, the A is sitting right at the very end. The reason why you need to do this is because the models were trained with some borders. It's going to have a hard time identifying the characters at the side of the page unless there is a white border or the whatever the surface color is. So let's figure out real fast how to add in a missing border now. Now, to achieve this, what we're going to do is we're going to be working with that image we just created without any borders at all. So what I want to do is I want to start off by grabbing the color. Now, the color that I'm going to specify is an RGB. I want this to be white, so I'm going to do 255, 255, comma 255. If you want to learn about RGB colors, I encourage you to explore them. Essentially, it's a way of creating, I think it's somewhere around 16 million different colors per pixel. This is how all your modern day TVs work, with the exception of specialized monitors. So the next thing we're going to do is we're going to specify the borders themselves. We're going to say top, bottom, and we're going to say left, right, and that's going to be equal to 150 times 4. So we're going to create a border that's a width of 150 for all sides. Now what we need to do is we need to create the image with border. We're going to make that equal to cv2.copy make border. This is how you make a border in OpenCV. We're going to pass in that object that had no borders that we just created a second ago, top, bottom, left, right, and then we're going to do cv2.border underscore constant, and the value is going to be set to our color. This is going to be our, in this case, white color. What we're going to do now is we're going to say cv2.im right, and we're going to pass in two objects. The first is going to be temp, and we're going to call this, let's call it image with border.jpg. We're going to pass in image with border, and then we're finally going to do our display temp image with border.jpg. Regretting that name now, having had to type it out so much. So let's load all this stuff in and let's run it. And we now have a white border that is much, much larger. So this is how you get rid of borders. This is how you add borders. Both of these are going to be necessary steps in pre-processing to achieve better OCR results. Now, these are not all of the things that you're going to have to do. I'm not going to cover transparency and alpha channel in this video because it will be a little tangential. If you want to know about it, leave me a comment or question in the comments down below. Essentially, it's going to deal with when you're getting a problem with certain PNG files. But for right now, I think this should cover all of the basics for how to manipulate images in mass to have better OCR results. In the next video, I'm going to introduce you to PyTesseract to show you how to start taking these pre-processed images and now running them through PyTesseract. And we're going to see how each of these different images results with OCR. And I'm also going to introduce you to the key values that you can pass through PyTesseract to actually account for different types of text. That's going to be all in the next video as we learn the ins and outs of PyTesseract. All of this will set us up for part 3 of this series, where we explore concrete, complex problems with OCR, handling text in different font styles, handling text that is organized in columns, handling text that is in tabular data in cell format. We're going to be addressing all of these concrete, narrow problems in part 3 of the series. That's going to be it for now, though. Thank you for listening. If you've enjoyed it, please like and subscribe down below. And as always, thank you to my Patreon supporters. And if you enjoyed this channel, you found this video useful, please consider subscribing and contributing via Patreon. And you can find that in the link down below.